So welcome back, everyone. Last time we almost finished this lecture. We were talking about the so-called random oracle model. And let's recall that random oracles are idealizations of hash functions, right? Typically in cryptography, the security requirement we have of hash functions is collision resistance, given by that experiment that we saw last time, right? Where an adversary gets a key for a hash function and wins if he finds two pre-images which collide on the same output or which map to the same output. And this property is good enough for a lot of applications. The light, yeah, better. Good. This is good enough for a lot of applications, but for some it isn't, right? For some applications, we want to use hash functions as if they were something almost like a pseudo-random function, right? Which they cannot be. Once you have the key of a pseudo-random function, it's not pseudo-random anymore, but still we want to have a behavior of hash functions that sort of approximately random, and that's captured in the random oracle model, right? And we know a few, let's say, magic tricks we can do in the random oracle model that are provably impossible in the plain model, or with meaning with any real-world hash function you might come up with, right? In theory speak, this is called the uninstantiability or unsoundness of the random oracle model. So complementary to that, for some applications where we classically used random oracles in proofs, we found actual real-world constructions that also lead to provably secure constructions. Okay, but so much for that. So much for the random oracle model. Finally, I haven't yet talked, or when I defined hash functions, right? I introduced a variable length hash function, a hash function which takes an input of any length and hashes it down to something short, something of fixed length, and a fixed input length hash function which takes something like of length 2 lambda and compresses it down to something of length lambda, right? So let's assume for a moment we had such a fixed length hash function. Question now, or fixed input length hash function. Question now is, can we use this to construct a variable length or an arbitrary input length hash function, right? And I mean, without much ado, right? Let's say we have a 2 lambda to lambda hash function. Question is, for instance, can we construct a 4 lambda to lambda length hash function? What's the natural idea?
Just apply this function. Why?
Yeah. So the idea, in a way, is to recurse, right? And that. I mean, back in the days, this was, or still to this day, those two result, one result by Ralph Merkel, the other one by Ivan Damgor, are still heavily cited papers. But let's say from today's perspective, this is yeah, sort of a somewhat simple thing. Ivan even says that, right? I never imagined that this silly little paper would have such an impact. But here, let's just talk about a very simplified version, right? So here I'm saying I have a hash function, a keyed hash function, which compresses 2 lambda bits down to lambda bits. And I want to use this to construct a new hash function that compresses 4 lambda bits down to lambda bits, right? That has a stronger compression. The first one has a compression factor of 2. The new one that I'm building has a compression factor of 4, right? And once you see how you get from compression factor 2 to compression factor 4, it's not that hard to see how to get to any compression factor, say 2 to the k, or doesn't even have to be a power of 2. And the idea is the following. Let's say we have such a hash function, right? And let's assume this hk. This hk, and let's assume it is collision resistant, right? Then my claim is that this new function is a prime, sorry, no, one prime too much. This new function, hk prime, which now comes from 2 lambda down to length lambda and is defined by, well, it takes, let's say we take the input, which is which is a string of length 4 lambda, and we split it in 2 parts, right? Let's call this x. Let's call this x, and we split it into 2 parts of equal length, x1 and x2. And what we do now is we first run our hash function hk on x1, which compresses this x1 down to a string of length lambda. And then we run hk on x2, which also compresses x2 to some string of length lambda. And I don't know if I've used this notation before, but whenever I use these 2 horizontal bars, this means concatenation, right? Concatenate strings, just in case I haven't used it before. So we concatenate these 2 outputs and hash them again, right? And here's a nice picture, sort of if we have our x up here, right? So we split it into x1 and x2, hash it, get hash values h1 and h2, concatenate them, and feed them back into the hash function, right? Feed it back into the meat grinder until we get something very, very small. Okay, now, good. The theorem says this is collision resistant. How could we reason about this? How can we, let's say, come to the conclusion that if H is collision resistant, then this H prime is also collision resistant? What's our way to approach this? How do we? Yes. Yeah. So that's the first step. That's the first step. Assume H prime is not collision resistant. What does that mean? What does it mean, not being collision resistant? So, I mean, it means we have an adversary A, right? A PPT exists PPT A such that here I have my adversary. What do I have to give him? We give him a key, exactly. So we give him a key K. And what does he spit out? What's his output? Exactly. So he gives us a hash collision for hash collision for H prime K, right? So he gives us some, let's say, x1, x2, comma, y1, y2, such that hk prime of x1, comma, x2 equals hk prime of y1, y2. Okay, good. So what can we do with this? What can we do with this adversary? We're looking. What are we looking for? We're trying to build an ad. Yes. Yes.
We should use it to break H.
So yeah, how do we, let's assume, right? We have our adversary and we're getting, let's say, a hash value, right? Which zip, let's just write our H prime out. So here you have HK, this is H prime of K, right? Oops. So let's call this H1, H2. Whoops, now I drew it upside down compared to before, but what gives, and here I have either X1 or Y1, and here, here X2 or Y2, right? Let's draw them in different colors to make things a little bit clearer. Let's draw X1 and X2, or Y1 and Y2, right? So let's say, let's say let's do the analysis by picture. Let's say X1 hashes down to H1, X2 hashes down to H2, and Y1 hashes down to H1 prime, and let's call them X1 prime and X2 prime, then it's better, H2 prime. All right, so we have X1 hashes down to H1, X2 hashes down to H2, and H1 concatenated H2 hashes down to H, but also H1 prime concatenated concatenated H2 prime hashes down to the same value, right? So this H is the same result for the green and for the orange one. What can we now argue? What can we do with this hash collision? We could go through a few cases, right? So the thing that we know is, if we go back one page, X1, X2 is different from, let's call it X1 prime, prime, X1 prime, X2 prime, right? How can we rephrase this? That if two vectors are different, what does it mean? Yes?
At least one of the elements are different.
Exactly. This means X1 is different from X1 prime, or X2 is different from X2 prime. Okay, so either we have here, this is option 1, and option 2 there. Okay, good. Now let's do a case analysis, right? What would let's do case 1. Case 1, I'm going to say this is H1 equals H1 prime. What happens in this case? Yes?
On the collision on the left side.
Yeah. So in this case, zip, we have a hash collision here, right? Then you have H K of X1 equals HK of X1 prime, but if they are different, then we found a hash collision. Okay, if they're different, if X1 not equals X1 prime. So what do we do if they're the same? Well, then we have to sort of go into a case 1.1, right? And look. So if they're different, then we're done, right? If they're different, done. If not, we have this case 1.1, and which case is this again?
X1 is not equal to X1 prime, then X2 must be the same.
Exactly.
As X2 prime.
But now, good. No, if let's say X1 equals X1 prime, right? And in case 2, we have now, it must hold that X2 is not equal X2 prime, right? And now again, we can slightly go down a case and wonder, let's say the next case, if H2 is the same as H2 prime, then we have HK of X2 equals HK of X2 prime, and therefore we have a hash collision, right? That's a hash collision. But then again, it can still happen that H2 not equal H2 prime. What happens in this case? Sorry, not equal. Else, if H2 not equals H2 prime, where do we get a hash collision now from? Then, well, then H1 comma H1 H2 not equals H1 H2 prime is a hash collision, right? Because we know that in the end this maps to our hash value H, right? So essentially, now we've sort of walked through the entire tree. I mean, a case that I left out is sort of the symmetric case to this, right? It might be, or actually, is this already? No, this is actually already. This is already the complete case analysis, right? If we let's say if H, oh, okay, good. One case is still missing, right? What do we if the case 1? I mean, I think I don't have extra space here. Last case is H1 not equals H1 prime, right? But that one works analogous to the H2 not equals H2 prime case, right? And I think I haven't done this very orderly in this picture, but I hope what becomes clear is that if this double hashing produces a hash collision, then we must have an inner collision somewhere, right? So if you sort of concatenate functions in this style or with one another and the overall function collides, then there must be an inner collision somewhere. Okay, good. And right, if we go one back, our adversary A prime, zip, he also gets this K, just outputs the pair that collides. Put the pair that collides. Okay, for HK. Good. So much for the extension of hash functions. Let's wrap this up. So we've seen that hash functions compress objects into, how did that happen? Into hash functions compress objects into short digests, right? You get a large object, maybe several gigabytes in size, and you want to compute a very short handle, which in a well-defined computational sense uniquely identifies this object. And for that, we're using hash functions. They are only computationally unique, right? We've seen that if you had unlimited power, then you could find a collision, right? Then you could find a handle which points, let's say, to two distinct large objects. And we've captured this by the collision resistance properties. Random oracles are an ideal or model ideal hash functions with much stronger properties and allow for easy proofs. But as I try to elaborate with a lot of words, the random oracle model is a heuristic. Right? If you give me a proof in the random oracle model, it doesn't necessarily hold in the real world for a real world, truly existing hash function. Okay, good. So much for hash functions. Let's do where is it here? Okay. Good. On the window. Okay. Okay. Oh no. Then let's try to save a copy. Otherwise, okay. That is unexpected. That didn't happen before. That saving still online? No. Yeah, but that saving creates such pains. Huh. If I force quit that now, probably we're gonna lose my annotations, which let's maybe make the 5-minute break now, because let's see what happens here. I think it is time to resume. 5 minutes are over. So the gods of Microsoft PowerPoint were not on our side and did not save my annotations, but let's see. I mean, maybe I'll just redo it after the fact, and then we have this consolidated on these slides. But okay. Good. Now let's move on to the next topic. So now that we've learned what hash functions are, right? Hash functions are a tool to guarantee the integrity of messages, right? That so if someone let's say that when we have a short handle to a big object, that this handle is in some sense unique. Now let's look into the problem of establishing authenticity, right? What does that mean? It means making sure you are talking to the person you are really expecting to talk to, right? Let's look into the problem of making or creating authenticity, right? And this is known as authentication. So we're still in the second quarter here. And before we go into the day's topic, right, let's recall that we've already seen a problem relating to authenticity, right? We had this example of these two generals who want to attack a castle, and in order to win, they have to attack exactly the same time. They have to sort of concentrate their forces or be outnumbered, right, by the enemy. If first this guy would attack, then that guy, then each of them individually would be outnumbered by the enemy, but if they attack together, they outnumber the enemy. So in order to do so, they have to coordinate, right? And the example we looked into was, let's say these two guys are using a one-time pad, and let's assume the keys are really secret, so no one stole this key, capital K, and now they want to talk to one another, right? This knight up here wants, or this army up here wants to talk to this army down there, sends a message, but the message is altered during transmission, right? Somehow in the middle of the night, something is tampered on the message, and all of a sudden the second knight gets the wrong instruction, right? He wanted to say attack, but what he receives is wait, right? So what goes wrong here is that the guy on the left thought he was talking to the guy on the right. Yeah. Oh, sorry. Yeah. The guy on the left thought he was talking to the guy on the right, but the message was altered during transmission, right? So in the end, he was not really talking, the message that he received was not really the message sent by the guy on the right. This is a problem of authenticity, right? The message, or the encrypted message that he received, was not authentic. It was tampered with, as we say. Good. And what we need now is a mechanism, or what we want to study now are mechanisms that ensure that messages are authentic. And in other words, that means if a message is authentic, you can trust that this message is the message that was originally sent by the sender and was not tampered with during transmission. Right? Let's now maybe look into some more examples where we would really like this authenticity property of transactions. One of them, of message transmissions, one of them being bank transactions, right? Let's say you want to send a transaction to your over 100 euros to a friend of yours, right? Because like you owe them 100 euros. So you make an online transaction sending, say, a ciphertext, right, to your bank that encrypts, I want to transmit 100 euros to my best friend. So, but if this channel between you and the bank is not authenticated, someone could come, right, sort of go somewhere in the middle of your channel, like your internet provider, right? Let's say your friend who you is not really your friend, but your internet provider, and you're paying your internet provider's bill, and it could be 100 euros, right? You need to have something very fancy to have a monthly internet bill of 100 euros. Maybe you're using Starlink. So now your internet provider comes and tampers with your transaction, flipping this into a transaction that says, well, 1,000 euros, right? This would be in the interest of your internet provider if they're not caught doing this. And all of a sudden you pay them 1,000 euros instead of just 100 euros, right? But let's say a more or less a more technological and less tangible example are cookies, right? Now, what are cookies? Probably most of you know this better than I do, but let's say you're talking to Amazon, right? You're shopping for whatever birthday presents for your girlfriend or boyfriend, and the problem with the HTTP, at least the original HTTP protocol, is that on the server side this is stateless, right? So when you talk to Amazon or to the web interface, at least, not to the database in the back, but when you talk to the HTTP interface, you're talking to a stateless machine that doesn't keep a state of your shopping cart, what you've put into your shopping cart, and this is stored locally on your machine in a cookie, right? The session you're running will produce a cookie somewhere on your machine, and this cookie stores maybe the content of your shopping cart, right? But now let's say it's not just you on that computer. Maybe someone else could come and start tampering with your cookie, and all of a sudden, let's say there's additional things in your shopping cart that you yourself didn't put there. You don't pay attention, go to the checkout, and all of a sudden you're being sent stuff that you didn't order, right? This could happen if sort of someone in or some other program on your computer gets sort of access to this cookie. And this is something in a multi-user system which you sometimes cannot avoid, right? So those are two, let's say, use cases or where we can sort of see why we need something like authentication. And now the idea will be, so in order to make sure or to authenticate some message, you will have to be in possession of some secret, right? If you're not the let's say valid owner of this secret, you will not be able to authenticate messages. Okay, right? So we're doing something just like encryption. We also saw we need something like a key. But now we're not doing encryption, but authentication, right? And this will also be a keyed primitive. So let's formalize this. And as always, we start with the syntax of this notion, right? So we want to look into something that's called message authentication codes. And a message authentication code consists of 3 PPT, probabilistic polynomial time algorithms, gen, mac, and verify. Gen algorithm is a randomized algorithm which takes as input, as always, the security parameter encoded in unary and outputs a key K. The MAC algorithm is a possibly randomized algorithm which takes our key K and a message M as input and outputs a so-called authentication tag T, right? We call this authentication tag because it's like something that we can slap onto this object, right? Like a price, not a price tag, an authentication tag. You put your sticker or your seal onto some object. And we have a verification algorithm, verify, which takes the key K, message M, and a corresponding or purported tag T. And this is a deterministic algorithm which produces as output just a bit B, right? So this algorithm just says yes or no. The verify algorithm, given a key, a message, and a tag, tells you whether this tag is valid or not, right? This is the validity tester, so to speak, for your tag. And in terms of correctness, this looks now slightly different than what we had for encryption, right? And for encryption schemes, our correctness always asks that if we first encrypt and then decrypt again, we get the same message. Here, correctness asks that if we have any message M, right, and we generate ourselves a key K, then if we first compute an authentication tag by running MAC on K and M, and then verify this, this tag with the same key K and the same message M, then our verify algorithm always outputs 1. It always outputs valid or verify, right? That's the correctness requirement we have for message authentication codes. So far, so good. So what's the next thing we're looking into? Well, of course, security, right? Without security, crypto would be pretty boring. But here, let's first try to draw some inspiration from the examples that we've seen so far of what we want from message authentication codes, right? So how should we go ahead and formalize the security of MACs, right? This is what the people who introduced these notions that we're going to see in a few moments, this is the thought process they had to go through some 35 or whatnot years ago. Yes, a question?
With the definition of message authentication of the correctness, doesn't that some clause which says that verify should also return 0 if the message authentication code is wrong?
Oh, why? I mean, let's say for correctness, right? We're sort of assuming the whole world is honest, right? So no one would even think of trying to produce a wrong MAC for some message. So here, as a matter of fact, it's enough to look into what happens with honestly generated MACs. Right? Everything that happens with just 1 second. Everything that happens with, let's say, MACs that were unfaithfully created will be captured in the security definition. But you had a question.
Yeah, no verify method now is one for every. That's also correct.
That's a correct scheme, exactly. So I'm going to repeat this for the online audience. Yes. That's the observation from the audience here was that a message authentication code where the verify algorithm is the constant one function is in fact a message authentication code with correctness, right? Let's see if this thing would also be secure, but it would be correct, right? In the very same way that, let's say, an encryption algorithm, which just outputs the plain text, decryption also just outputs the same plain text, is a correct encryption scheme, right? A encryption scheme which doesn't do anything is correct, in the same sense that a message authentication code where the verify algorithm always outputs one is also correct. There was a question from the online audience: why is authentication and not integrity check? Well, I didn't choose these the names, right? Sort of this is what the wisdom of the elders converged upon, and those are the names they came up with. And sort of the technical term, right, is just authentication or message authentication code, right? Of course, there's say natural language equivalent notions or words that carry the same meaning, but let's say the technical term for this is message authentication codes, right? If you think computer science or crypto is bad in giving names to things, ask the mathematicians who grow sheaves and or whatever on rings and fields, right? The nomenclature in math is way more colorful and less grounded in an actual application than what we have here in computer science. Okay. There was another question: does it specify who is the sender? I mean, right now we just have the syntax and correctness requirement, right? Syntax just says, here are the following algorithm. Who runs which algorithm? Well, this has to sort of become clear then from the application. But we are still in a symmetric key scenario, right? Where sender and receiver, once we have sender and receiver, could be the same person, right? Have the same key, right? And sender and receiver, I mean, again, this could be the same person, this could be yourself. You put something on your hard disk and authenticate it. And now 10 years later, you come back and want to read this old piece of memory. And in order to make sure that no program or infiltrator tampered with your old memories, you first check the authentication tag. If it's still, if it is valid, then you can make sure that this is that those are authentic memories of yours. So who's the sender and receiver really depends on the application, right? Good. Now let's try to reproduce this thought process that the people who probably already 40 years ago came up with the security notion of this. The first question they asked is, or they wondered is, well, okay, let's say such an authentication scheme is under attack, right? What should an adversary be able to see, right? Are we do we expect any kind of secrecy from message authentication codes? Not really, right? This all happens in public. These are like, here's my computer. I'm putting a tag on it, says it's mine. This is all happening in broad daylight in public. So we can safely assume that a real-world adversary sees authenticated messages or authentication tags that were generated with my key, right? Because I'm not keeping these authentication tags secret, right? So a real-world adversary who wants to impersonate me or whatnot, before he tries his impersonation attempt, he might collect a lot of my authentication tags, right? This is something we probably cannot safely prevent, right? So let's go one step further and say, okay, I cannot prevent that the adversary sees authentication tags of some messages under my key, but who chooses these messages, right? What distribution do they come from? Well, for real world applications, this is pretty hard to capture, right? I mean, if let's say the distribution of messages, if we wanted them to be somehow random, this would be really hard to capture. So it's quite conservative to say, well, let's just let the adversary choose the messages, right? In the real world, maybe he cannot choose them, but if we let him choose these messages, we're erring on the conservative side. Right? We're not making too strong of an assumption that he would never see an authentication of this or that message, but yeah, we are sort of on the safe side if we say, hey, instead of trying to go over all possible distributions, let's just let the adversary pick the messages of which he wants to see authentication tags himself, right? And this is pretty much in the same spirit as we had in CPA security, right? In CPA security, the adversary gets an encryption oracle where he can query any polling number of encryptions of messages of his choice. And here we're going to say, well, the adversary shall have an authentication oracle which authenticates any message of his choice. Okay, now we know now we have an understanding of what resources we want to provide to the adversary, but what's going to be his goal. So far, for encryption schemes, the goal of the adversary was to distinguish, right, whether a ciphertext encrypts M0 or M1. I mean, here there's no secrecy of the messages or the tags. What's the goal of the adversary?
To change the message without changing the tag, maybe?
To change the message without changing the tag, that could be, that means I am giving you a message together with a valid tag, and you would win if the tag stays the same, but the message becomes different. That would be a valid notion, but authenticate a message, precisely. His goal is to authenticate a message. However, he has an authentication oracle, right? He can query, I mean, if the goal was just to authenticate a message, then he would just pick a message, send a query, an authentication tag, and output that. That can't be a valid attack, right? Because so far he has just been using his, let's say, valid resource. He hasn't done any magic. Come again? Another message. That's precisely the thing, right? So in the real world, the goal of an adversary might be to authenticate a new meaningful message, right? 1,000 euros instead of authenticate the transaction of 1,000 euros instead of 100 euros. But we don't want to capture, we don't want to put, let's say, some specific types such as money and euros into our definition. So in our idealized security definition, or in our model, right, we say, well, he wins if he manages to authenticate any new message. Okay, so what he gets as a resource is an authentication oracle, which authenticates him any message of his choice, M1, M2, M3, M4, M5. But now he wins if he manages to compute a valid tag on a new message M star, which is not in the set M1, M2, M3, M4, M5, right? Because for those he knows already tags, if he, so he wins if he manages to somehow find a tag for a message for which he hasn't seen a tag before, right? And this is sort of a pretty conservative attack goal. And as always, let's look at, or a pretty, let's say, yeah, pretty conservative attack goal. Let's look at this as always in a picture. So the security notion for message authentication codes will be something called existential unforgeability under chosen message attacks. Don't worry, it's gonna show up on the right in just a moment. And we have the following EUF CMA experiment between, as always, our challenger and an adversary. So let's say A is a PPT adversary. Our challenger does the following. First, he generates a key. And next, the adversary gets access to a MAC oracle where he can send an MI and gets back MAC K of MI, and let's call this TI. Okay, he can do this any poly number of queries. Okay. And let's call them M1 to MQ. Okay, so we record the queries. Let's say maybe a challenger here, record queries M1 to MQ, record all queries. Okay, and later on, the adversary outputs an M star and an attack T star, and we say he wins if his message M star is not in the set of messages that he queried to his MAC oracle, and if verify K M star T star equals 1. Okay, so if those two conditions hold, if the message M star is new and the tag T verifies, then the adversary wins, otherwise he loses. Okay, and we call the output of the, we call the random variable, which is just a bit produced by this experiment, we call it EUF CMA A of lambda, and oh my God, this is slow. We say a message authentication code gen mac verify is existentially unforgeable, right? EUF under, well, adaptive doesn't appear there, chosen message attacks. Here you have this CMA or EUF CMA secure. If it holds for every PPT adversary A, that there exists a negligible function nu such that for all security parameters lambda, the adversary's winning probability is bounded by nu of lambda, right? And here now we see how these what the convention for these cryptographic security experiments is. First, on the left side, the EUF is the goal of the adversary, existential unforgeability. That just means producing a new tag for any message of his choice. And on the right side, we sort of abbreviate the resources of the adversary. chosen message attacks, right? Goal resources, existential unforgeability under chosen message attacks. Compare that to int CPA. Goal distinguishing or indistinguishability, or resources chosen plain text attacks, right? Where it gets an encryption oracle. And there's many more of these things and or of these notions, and they get wildly complicated, but what they all have in common is in this short notation, first we sort of give a quick abbreviation for the goal and then state what resources we give to the adversary, right? Those are the two things which we by now understand that matter. So let's come back to your question. What about outputting 0 on arbitrary messages? Once we require this once we require this security notion from a Mac, what does or what can we say now if on which messages should our Mac or on which tags should our Mac output 0? So the suggestion earlier for a correct Mac was a verify function which almost always outputs, which basically always outputs 1, right? Now let's assume we have a message authentication code that satisfies this security notion, yes?
Then the verify function should only output 1 if and only if the message fits the authentication code.
Yeah. So the answer from the audience was then, in this case, the verify function should only output 1 if this tag T was indeed computed by Mac K of the message. In other words, that means for this security notion here implies that for almost any tag T, right, for almost all tags T, this verify function should output 0, right? Because otherwise, here would be an attack. I have a message, just choose a random tag without ever querying the Mac oracle. If that verifies, right, then you win already in this security experiment, right? So this security notion in and of itself already requires or demands that the verify algorithm almost always, or for almost all choices of T, has to output 0. So no extra correctness requirement needed. Let's be theory efficient here. Good. Do we have questions before we move on? Let's look to the online audience. Don't see questions there either. Good. So intuitively, this notion here could already capture everything one might want to expect from a message authentication code, right? It says, well, in order to win, you have to find a valid authentication tag for a new message, right? But it turns out, and it also took cryptographers a while to find out that sometimes maybe we also want to say something about this this tag T in the winning condition, right? So here, let's say I have the following attack. I am querying a message M to my Mac oracle and get back a tag T prime. And now I am, let's say, somehow coming up with a new tag T prime for the same message M, right? So even I have already seen a valid authentication tag, but I somehow managed to turn this into a new authentication tag T prime for the same message. Here, this would not be a valid winning strategy, right? And one might ask, is this a winning strategy? After all, you've already seen a tag for this message. So here, finding a new authentication tag for a message for which you've seen a tag will not make you win, right? But this is captured in the so-called strong unforgeability experiment, right? Where basically it becomes strongly unforgeable in that we've sort of relaxed the attack goals of the adversary. So we made the adversary's life easier. Therefore, the notion that we get is stronger, right? So in this strong notion, the adversary wins. So here we don't just store query answer pairs, right? M1 T1 until MQ, right? And here the adversary wins if the message tag pair that he produces is not in that previous list. So now it is a valid winning strategy to reuse a message that has been used before, or that he queried to his authentication oracle, but add a new and valid tag to it, right? Sort of, if you can manipulate the tag, can manipulate a valid tag, you win now. Yes, a question. K is chosen once in the experiment. Exactly. So the question was, is K only chosen once? And the answer is yes. We choose one single key and get, and this key, right, is the one that we use in this MAC oracle here. Okay, so this is strong unforgeability. I mean, as I said, it took cryptographers a while to hone in on this slightly stronger notion. I mean, it's clear that a scheme that is strongly unforgeable or strongly existentially unforgeable is also existentially unforgeable, right? Because if you have an adversary that breaks this experiment, it automatically also breaks that one. Okay, good. All right. Good, and now let's quickly see how in, say, these applications that we've seen, we are supposed to use message authentication codes. So let's again say you want to send something, some transaction to your bank, and you want to say it's the message is 100 euros from Bob to Alice, right? That's sort of the transaction you want to do. And now our hacker sort of cannot change the content of this message anymore, right? Here, let's say both Bob, actually, no, not that bad. Bob and the bank have this key K. Okay, now let's say this happens, but we're not encrypting, we're still not encrypting this message, this authenticated message. So if we have an eavesdropper, he can still record this transaction, right? And whoops. One thing that such an eavesdropper now can do is just replay this transaction, right? So first you did it, but someone listened in on this transaction and stored it, and now they can just replay your transaction at some point in the future, and it looks like you were sending this thing again, even though it was some outside hacker or whatnot, right? Message authentication codes don't protect you against replay attacks, right? We've even in the security experiment, we've given the adversary this authentication oracle, where he can produce authentication tags for messages of his choice. In the real world, no one prevents an adversary, or nothing about message authentication codes prevents an adversary from reusing messages he has seen before later on, right? So message authentication codes do not prevent or protect against replay attacks. Okay, so for that, we need additional measures, something like a timestamp. So we're not just authenticating the message, but also when the message happened, right? So now a better way of using this, right, or using authentication codes is not just, let's say, to authenticate what you want to send, but also when, right? If I put today's date, and all of a sudden, let's say in 2 or 3 days, someone else comes with the same thing, but the timestamp in this message is today, that's not going to be valid, right? But this is an additional, let's say, mechanism on top of authentication codes. This is typically not modeled on the cryptographic layer, right? So in the cryptographic layer, when we talk about message authentication codes, we want to keep things as simple as possible. And let's say the typical necessity of adding something like a timestamp only comes in on an application layer. Okay, so this is something a very reasonable security aspect that is not immediately captured by message authentication codes. Good. Okay, but now that we've seen what MACs are and how we should use them, how we should maybe not use them, question is, yeah, how do we get message authentication codes, right? How can we construct MACs? Okay, and let's again try to relive or whatever the wise people who conceived these constructions thought, and let's sort of consider the constraints we have a bit. So on the one hand side, in terms of security, it should not be possible to find an authentication tag for a new message for which you haven't seen a tag, right? And let's try to match this somehow against the list of cryptographic tools we have seen so far, right? The list of low-level primitives. And now, to translate this maybe slightly differently, what we kind of need is, let's say, a function which is unpredictable on new inputs. Now, what could that be? Any suggestions? A random function, that's good, but typically random functions come with a drawback that they're pretty big to store, right? That you have an entire function table. So we would like to have something more compact than a random function. But random functions are good. Security-wise, they're good. So any other suggestions? Pseudo-random functions, exactly. It will be the workhorse of cryptography, pseudo-random functions, right? And for now, we will assume that we only want to authenticate messages of fixed length, namely n bits. I wonder how we might later compress long messages down to n bits, right? Foreboding, but let's look at this construction. I don't know why this still has numberings, and let's say PRF, which takes a key and an input and outputs lambda bits, or lambda bit string, is a pseudo-random function. And now our gen algorithm just chooses a key k, which is a lambda or security parameter bit string uniformly at random, right? So my MAC key is now just a PRF key. And to evaluate my MAC, I'm just computing the PRF, right? What do I do to verify? Now, if I give you a tag, you have the key. Now you have the key K, message M, and tag T. How do you verify? Yes.
You just compute the MAC again to a bitwise compound.
Precisely. So what you do is you just recompute PRF KM and compare it to T. If they're the same, you output 1, otherwise 0. Correctness, it says on this slide, is canonic. Now, why is that the case, right? T equals MAC or PRF KM is unique for M, right? For message M, there is only a single, for message M and a key K, there is only a one unique tag, right? As, I mean, in other words, MAC KM is deterministic. Oops. Typically, establishing the correctness of deterministic primitives is just realizing, oh yeah, I'm computing this function here, I'm computing it over there. They're deterministic. They do compute the same thing. Okay. But now, what about security? And obviously, the security also follows somewhat directly from the security of the underlying primitive. If PRF is a pseudo-random function, then the construction that we've seen, then let's just write, let's call that gen mac verify, is a strongly, right? I don't need to write strongly twice, a strongly EUF CMA secure MAC. Right, and in a way that's cool, right? We converged onto this notion of pseudo-random functions with the need of building in CPA secure encryption, right? Encryption where we can reuse the key arbitrarily, right? This sort of led us to the notion of pseudo-random functions, and look there. They also turn out to be incredibly useful for, let's say, a completely orthogonal task, namely authentication, right? We sort of invented PRFs to achieve a privacy notion. Now we're using them to achieve an authenticity notion. Okay, so that's a kind of a a cool synergy, so to speak. Maybe with the proof, we still have 5 minutes. I'm just starting with the first page, right, where nothing interesting happens. Again, we'll approach this via contraposition, namely assume gen mac verify was not SEUF CMA secure. Right? And goal is, of course, a goal show that this implies that PRF is not pseudo-random. Right, and the way we go for this is if mac, let's call this mac not SEUF CMA secure means there exists a PPT adversary A and a non-negligible function epsilon and a non-negligible epsilon such that probability that A wins in this EUF CMA experiment is greater than epsilon, right? The adversary has non-negligible success probability. Sort of theory speak for often big success probability. But okay, before I'm doing these drawings, I think let's call it a day for now, and let's hope the slides are gonna save. Oh God. Whew. Okay, yeah, this time it worked. He saved the slides. Good. Let's. Oh, I see. There's one more question from the online audience. What holds back the attacker from modifying the timestamp to be as he requires to be? Good. We still have maybe 1 minute. Can anyone answer me that? Yes. Exactly. So what stops the attacker from changing the timestamp is that the timestamp is part of the message that we have authenticated in this example earlier. But that's it for today. Thanks, everyone. Let's stop the recording.